So the swept-wing T-tailed transport became a reality. Due to design trade-offs necessary to meet the user's requirements, this type of transport incorporates unique flight control and stability characteristics. A pilot flying the swept-wing T-tail has got to know its limitations, and as in all flying, he's got to stay ahead of his aircraft. There's no doubt that pilots transitioning from conventional aircraft to T-tail swept-wing jets have some pleasant and interesting experiences in store. A great many pilots are changing over to the swept-wing T-tail C-141, so this aircraft will be used for demonstration purposes. But keep in mind that the flight characteristics depicted in the C-141 tend to apply to all jet transports of similar design and configuration. Now let's meet our flight crew. Just finishing the pre-flight are the engineers and the loadmaster. They are joined by the rest of our flight crew, the co-pilot and the navigator. The aircraft commander? We thought you'd be wondering about him. Well, you can't see him objectively because he is you. You're going to see this film as if you yourself were sitting in the aircraft commander's seat. First, the T-tail. Ever see a tail assembly this high off the ground? This feature facilitates aft ground loading. Also, the high tail reduces the danger of structural damage during all types of loading operations. You're probably thinking, won't a tail that high present inspection and maintenance problems? Frankly, yes. But as already indicated, during the design phase, it was determined that the advantages of all the special features on this aircraft offset apparent disadvantages. At your stations in the cockpit, you and your crew are completing the before takeoff checklist. On the radio, you hear the tower clearing the aircraft just ahead of you.
Cleared for takeoff.
Let's observe its takeoff. Here's a chance to note some features peculiar to swept-wing transports. As already indicated, design or special mechanical devices permit a shorter roll. During takeoff, roll, and rotation, the aircraft commander must take into consideration that he's piloting a plane with swept wings. When a crosswind is present, he must exercise special care, for crosswinds produce a control problem due to the rolling action generated by uneven airflow over the wings. The upwind wing develops more lift than the downwing. At rotation, swept wings provide less clearance than straight wings. With a crosswind causing roll, the tip clearance problem is amplified. Many pilots often confuse aircraft attitude with angle of attack. What's the difference? This is the aircraft's attitude, the relationship of its longitudinal axis to the horizon. And this is angle of attack, the relationship of its longitudinal axis to the relative wind. Except for disturbances, the relative wind is 180 degrees from the direction of flight. See the difference? It's important that you learn and remember this difference. Now we're airborne and have caught the aircraft in front of us. With this good view of the configuration, let's point out some swept-wing advantages. Sweeping the wings gives the aircraft higher cruise speeds. You know why? Compared with the straight wing, the swept wing delays shockwave development because the wings are swept and are usually lower aspect ratio. The speed at which shockwave occurs is called the critical Mach of the wing. It is this shockwave which induces drag. So by delaying the shock formation, the aircraft can attain a higher cruise speed with the same amount of power. Here is actual shockwave formation on a swept wing during a high-speed test flight. As a pilot, you've got to be aware of certain limitations in this type design, which up to now you probably haven't considered. You're flying a jet with a more flexible airframe at much higher speeds. you're more apt to experience high-speed buffet. The builder must give more consideration to the prevention of control flutter. You will find that aircraft are built with features which delay buffet and prevent flutter, such as a clean airframe with a good airflow pattern and dynamic balancing weights installed on control surfaces, as determined by wind tunnel tests. To verify aircraft structural integrity, the builder conducts extensive flight tests up to limit speeds, with mechanically induced oscillations as pictured here. Flutter will not occur within the aircraft's operational envelope. Incidentally, most transports are designed and built so that it's very difficult to get buffet in level flight, even with maximum thrust. A flight condition swept-wing pilots must be aware of is Dutch roll. To induce Dutch roll, the aircraft must be displaced in yaw or roll from normal flight attitude. This creates a yawing, rolling action which may continue and increase in amplitude. Don't be guilty of getting yourself into this situation through abrupt and uncoordinated control movements. If Dutch roll is encountered, it can be stopped by proper use of the ailerons, rudders, or a combination of the two. Recovery using a coordinated combination of the controls is generally preferred. Also, descending into denser air, thereby increasing airspeed, will help correct Dutch roll. Dutch roll can also be created from atmospheric disturbances, such as turbulence. Some transports are equipped with stabilization augmentation systems, such as yaw dampeners, to counteract Dutch roll. The extent to which Dutch roll is likely to be experienced varies with different aircraft. The greater the sweep of the wing, the greater the tendency for Dutch roll. So study the flight manual for your aircraft to learn how to counteract this flight condition. Designed to fly in the transonic range, jets are subject to another flight problem, tuck. With the aircraft approaching critical Mach, the lift moment shifts aft, causing the jet to pitch down or tuck. Most planes are provided with Mach trim compensators, which automatically trim the aircraft to counteract tuck. If such devices are not available, trim the aircraft yourself. The amount of tuck varies in different airframe designs. The T-tail provides jet transports with advantages. Unlike the low-mounted stabilizer, the T-tail is designed to operate above wing, fuselage, and engine disturbances. Since it is operating outside disturbed air and placed at the end of a longer stabilizing arm, less control and stability surface is required for effective operation. Therefore, the high T-tail can be smaller and lighter than the lower empennage, reducing the aircraft's basic weight. This smaller T-tail, but with the same capability as the lower assembly, presents less exposed surface or wetted area immersed in the atmosphere to create less parasite drag. Less drag gives more mileage for the same amount of fuel used. The total weight savings from the lighter assembly and reduced drag enable the aircraft to carry more cargo. This is commonly called mission productivity. And look how the high T-tail facilitates aerial delivery capability. You'll find the T-tail assembly easy to handle with excellent control responses through normal angles of attack and flight attitudes. But you should be fully aware that when flying a swept-wing T-tail jet transport, you'll have no difficulty attaining high angles of attack. Actually, in a swept-wing jet, your angle of attack in any flight regime can be greater than in a straight wing before total wing stall develops. When the angle of attack is great enough to subject the T-tail to downwash from the wings, fuselage, or engines, the aircraft will tend to pitch up. The degree of pitch up is a function of the particular configuration. So couple the T-tail to the swept wing, and you've got a new stall problem. The lift moment on a swept wing shifts forward as the angle of attack increases, usually around maximum lift, and the aircraft will pitch up. Combine this pitch up with a pitch up resulting from downwash, and before you realize it, the T-tail can be completely enveloped in the downwash. Constant pressure by the pilot on the yoke after tail envelopment can cause a greater elevator displacement due to the lighter aerodynamic loads aggravating the situation. When this occurs, the T-tail assembly, designed to operate in clean, undisturbed air, may lose partial elevator effectiveness. It is during these high angle of attack stalls that heavy buffet usually occurs, applying heavy local and structural loads on the entire aircraft, particularly on the horizontal stabilizer. The problem is twofold, either structural, due to heavy induced loads, or performance, from a lack of elevator stabilizer effectiveness at this high angle of attack, which could result in the loss of a great deal of altitude. Here is a vivid illustration of the results of structural overstress experienced during wind tunnel testing. Anticipating such problems, the designer has taken such corrective steps as beefing up assembly components sufficiently to enable the aircraft to withstand heavy structural loads, improving response capability by augmenting unpowered controls with electric or hydraulic power. Obviously, the most logical way to combat critical stalls in flight is keeping yourself out of them. Again, the designer has come to your aid. He's equipped the aircraft with a stall warning and prevention system. Let's see what one of these systems can do for you. Various stall warning and prevention systems naturally have normal equipment differences and different pilot warning devices. Basically, however, they all operate in a similar manner. On an airplane equipped with one of these systems is a mechanical device which detects the plane's angle of attack. During flight, this detector relays the information it gathers to the system's computer. From this and other inputs, the computer automatically determines when the aircraft is approaching a critical situation. The system then activates a stall warning device. On aircraft with a stick shaker, this shaker vibrates the stick, or yoke, and simulates the vibrations experienced in conventional aircraft when nearing stall. If the angle of attack increases further, some aircraft have the system activate a prevention device known as a pusher, which forces the aircraft out of the approach to stall. No matter what you might have heard to the contrary, you can override the action of these systems at any time you desire. But be smart. Don't be a wise guy. Be a wise pilot. Have confidence in a system designed to give you a helping hand when you need it. When ready for final descent, how do you select a proper approach path? Briefly, the answer is good judgment. As you know, pilot judgment is based on vision and experience. If you're a new pilot transitioning to swept-wing jet transports, naturally, you've had little chance to gain experience in this type aircraft. On the other hand, perhaps you've flown swept-wing aircraft, but not enough to be completely familiar with their handling peculiarities, including those concerned with landings. Look at this other aircraft. We don't have to tell you that special mission and terrain requirements can cause deviations from the normal final approach. But we'd like to remind you that when flying a swept-wing transport, you'll have to plan your final with extra care. Inherent in this configuration are unique actions you should not only be familiar with, but know how to counter. Let's contrast a normal with an abnormal or steep approach in a swept-wing jet. One type of drag consistent with all approaches is parasite drag. On a clean airplane, parasite drag always decreases in proportion to the speed decrease as the aircraft slows down. However, during the approach, gear and flaps are extended. and friction causes a drag buildup on the frontal surfaces. On a normal approach, with the aircraft in a 2.5 to 3 degree glide path and a rate of descent 500 to 700 feet per minute, descent is controlled primarily by changing pitch and power and by holding attack angle relatively constant. Here, flare requires only a small change in angle of attack. The other type of drag we're concerned with is induced drag, which occurs during the final stages of approach. As compared with straight wings, swept wings can produce more induced drag because they are usually lower aspect ratio and can attain higher attack angles. Drag is the result of the lifting force exerting pressure toward the rear of the aircraft as the angle of attack increases. During flare, as pitch attitude is increased, the angle of attack increases. The higher the angle of attack, the greater the induced drag. Since during a normal approach little change in angle of attack is required, a small amount of induced drag is created and a safe landing can be made. With these concepts in mind, let's look at an abnormal or high sink rate approach. Usually your power is low or at idle. The attack angle is positive. As you near the runway threshold, you want to decrease rate of descent. You feel you can accomplish this by increasing the pitch attitude to increase lift. If on speed, you may also feel, incorrectly mind you, that no power change is necessary. Remember your engines are idle. Induced drag rapidly builds up due to the increase in angle of attack resulting from your pitch change. However, your lift is not increasing in proportion to drag buildup, and your rate of descent is not decreasing sufficiently. You suddenly realize the need for power. Your delay in power application, plus the lack of altitude, plus the inherent delay in jet engine response, will put you behind the power curve. Even with maximum power applied, the drag is now so great that the aircraft is beyond recovery. From this example, you can see that you don't have to be low and slow on final to get behind the power curve. If you must make steep approaches, use power and pitch, not pitch alone, to decrease your sink rate. Sufficient power should be applied to arrive over threshold with a normal rate of descent. To safely operate this type aircraft during this critical portion of flight, always stay ahead of your aircraft. Remember, gross weight and center of gravity drastically affect your recovery from sink rate, requiring more planning on your part. Know your aircraft's operational characteristics. You're going to perform more and more missions in swept-wing T-tail jet transports. One thing you can count on, they're going to be bigger and faster, and they're going to be more complex in operation. Here's a good example of the transport jet of the future. Hard to believe, isn't it, that one this big will even get off the ground? But it will, and you can be sure it will be equipped to do the job programmed for it. But remember, the flight characteristics we've demonstrated apply to all types of swept-wing T-tail jet transports. So when you find yourself in the cockpit of one, here are some particular points you'd better not forget. Plan ahead for your flight, and be sure you cross-check all instruments before departure. Avoid abrupt maneuvers at high angles of attack or at low speeds. Always stay within the equipment's operational limits. In today's modern jets, you can't depend on seat-of-the-pants sensations to accurately relay structural stress information. Therefore, keep your flight smooth. Avoid abrupt inputs to the control system. Never stall a swept-wing T-tail jet. Stall warning and prevention systems are on an aircraft for your protection. Use them. Plan ahead for approach and landing. And above all, take to heart the warnings about avoiding high sink rate. One final thought. When you're sitting in the aircraft commander's seat, keep in mind that the conservative pilot is the safe pilot.